Hello and welcome to another one of our online lectures for differential equations. And today we're going to be taking a look at homogeneous equations with constant coefficients. We're going to be talking about the characteristic equation in this one. So it's going to be the best. Starting off, we have a theorem for distinct real roots of the characteristic equation, and we'll talk about what this characteristic equation is. We say if the roots r1, r2, r sub 3, so on and so forth to r sub n of the characteristic equation, a sub n r to the n plus a sub n minus 1 r to the n minus 1 plus so on and so forth plus a sub 2 r squared plus a sub 1 r plus a sub 0 equals 0. If those roots are real and distinct, meaning they're real numbers and they're all different, then we can build a general solution to our differential equation by using those values for the roots as coefficients in the exponent. So we get y of x is some c sub 1 e to the r sub 1 times x power plus c sub 2 times e to the r sub 2 times x power plus so on and so forth plus c sub n times e to the r sub n times x power. And that's going to be a general solution of our homogeneous differential equation. Now, we did already kind of talk about this in the very first lecture. And the idea is that we're going to be assuming a solution of the form y equals e to the power of rx. Now, you might ask, why are we doing that? I want you to look at this first example. We have y double prime plus 3y prime minus 10 times y equals 0. And we start by saying, okay, what kind of function would most likely work out in this? There's a lot of things that probably wouldn't work. We want to know what kind of function could this possibly generate a true statement from? And notice that we're going to take y, multiply it by a coefficient, and then we're going to add to that y prime times a coefficient, and then we're going to add to that y double prime times a coefficient. And there the coefficient happens to be 1. But the idea is that we're building some linear combination of y and its derivatives, and we're hoping that it gives us 0. Now, keeping that in mind, a good question is, well, what function allows us to balance things in that way? Power functions wouldn't probably work because whenever I differentiate a power function, it becomes incredibly different. So for example, we know that if we start with something like y equals x to the fourth, the derivative y prime gives me 4x cubed, and these are not like terms. So if I'm multiplying by coefficients, I'm not going to get them to balance out to give me 0, right? I'm just going to have some weird looking combination of them. So that's not going to work. When we think about other functions, like natural log, for example, as soon as I differentiate that, it becomes very different. It becomes 1 over x, or x to the power of minus 1. If I differentiate that, it's going to give me minus 1 over x squared. These are very different, and introducing constant coefficients isn't going to allow me to balance those things out. Cosine and sine are good ideas as well, but I want you to keep in mind that, for example, when we differentiate sine, it becomes cosine. We differentiate that again, it becomes negative sine. So there is some semblance of it returning back to that original function, but in between, it introduces this new function, for example, introduces cosine when we started with sine. So that would be a little bit more difficult to work around with. And we start thinking about other functions. There are even nastier ones that won't work as well. Constants change when we differentiate them. But the idea is that exponential functions stay roughly the same, right? If I take e to the power of rx, if I find its derivative, well, the derivative by chain rule gives me e to the rx times r. So it really hasn't changed that much. The only thing that's different is now it has this new coefficient r. And if I differentiate again, I'm going to have r e to the rx times another factor of r, where this really just gives me r squared e to the rx. So if I start differentiating exponential functions, And in particular, if we think about e to the x, it never changes. But if we think about something like e to the 3x or e to the 4x, it changes, but not a lot, right? We still have that same exponential function, but just with a new coefficient. So it doesn't really change drastically at all. So keeping that in mind, we would say that our best bet for solving a differential equation like this, if we don't really know where to start, is to assume that y is some exponential function and to see if it works out. If it doesn't work out, then it doesn't work out. And the differential equation is going to tell us by showing us a bunch of nonsense, a bunch of garbage, some false statements. But if it is going to work out, then we should be able to solve. And that's where we're going to get this idea, this notion of a characteristic equation from for this lecture. So for y double prime, well, starting with y, we're going to assume y is e to the rx. We're going to substitute that in. But then for y prime, we're going to substitute r e to the rx. For y double prime, we're going to substitute this r squared e to the rx. So if I go ahead and plug this in, for y double prime, that's r squared e to the rx, plus 3 times for y prime, we have r e to the rx, minus 10 times y. For y, we're going to substitute e to the rx, and then equals 0. Now what I can do from here is I can actually factor e to the rx out as common. So we get e to the rx times, in parentheses, what am I left with? I'm left with r squared plus 3r minus 10, and then equals 0. Now if I'm trying to set this equal to 0, e to the rx, this is an exponential function, that's never going to be equal to 0, not by itself. It would need some help from the other factors. So we can, divide this over, we can just ignore it, we can neglect it, but really we're focusing on r squared plus 3r minus 10 equals 0. And this is what we refer to when we say the characteristic equation. The characteristic equation is this polynomial on r that we set equal to 0 and try to solve. So we say, okay, the exponential term won't be equal to 0, but the rest of this could be equal to 0, that r squared plus 3r minus 10. And if I can factor that, I want to factor it further. So let's see if this will factor, and it looks like it will. But here we said this is our characteristic equation. I can factor this, right? So we get r plus 5, r minus 2. And from this, we can solve for r. So if I'm solving this for r, that means r equals negative 5, and r equals positive 2. And so now from here, at the very beginning, we assumed that y was some exponential function e to the rx. Not only was that a good assumption, a safe assumption, but we also found out that it works for 2 values of r in the differential equation that we started with. It'll work for y sub 1, if you want to call it that, is e to the negative 5x, where r is negative 5. And it'll work for another one, call it y sub 2, where we have e to the 2x. So now what I can do is I can build from these 2 solutions to my second order differential equation, right? We started with an order 2 differential equation. So these are the 2 solutions that we were trying to find. I can build this into my general solution, just remembering that superposition principle, that y is equal to c sub 1 times y sub 1 plus c sub 2 times y sub 2, or here that y is equal to c sub 1 times e to the minus 5x plus c sub 2 times e to the 2x. And that gives our solution for us. And this is that case that we were talking about where we have these distinct roots. So here r was negative 5 and r was 2. They're not the same, but we do sort of approach this a little bit differently if we have, say, repeats or if something else happens. We're talking about, for a lot of these examples, we're talking about quadratics, but we will take a look at things of higher order too. So, we expect some of those usual things to happen. Speaking of which, we could have repeated roots. So our theorem here says that if the characteristic equation, and then there we have this polynomial on R of degree n, if that characteristic equation has a repeated root R of multiplicity k, then the part of the general solution of the differential equation of order n corresponding to that one specific root of multiplicity k will have this general form where we have e to the rx all the way out here to the side, but then we build this polynomial in front of it. And that polynomial is of degree k minus 1. So we build up to it, but we stop just sort of one shy of the multiplicity. And I think it can be a lot to sort of look at all at once. So I'll try to explain this in a way that I think makes it a little bit more intuitive and a little bit easier. But the same basic principle applies here, where we're saying, okay, here I have a differential equation where if I take some function y, multiply it by 9, add it to the derivative of that function times 6, and add that to the second derivative, I'm hoping that it gives me 0. So we think, well, what function would work? And it always comes back to that same idea that an exponential function is the best choice for us, hands down. So we'd say, well, then y could be some exponential function e to the rx, meaning that its derivative y prime with chain rule is r e to the rx. And the second order derivative just generates another factor of r by chain rule, so r squared e to the rx. And we would go and start plugging these things in to our differential equation. So we'd say, well, here, this is going to give us r squared e to the rx in place of y double prime, plus 6 times y prime is 6 times r e to the rx, plus 9 times y, that's 9 times e to the rx, and then equals 0. But as soon as we do this, we'd say, well, notice e to the rx appears as common, so we factor it out, and we're left with r squared plus 6r plus 9, and then equals 0. You're going to notice this is a common trend that we factor the e to the rx out, and then we sort of ignore it. So there is a quicker way to get to the characteristic equation, but for now, at the introduction of this material, I want you to kind of appreciate where it comes from. It comes from just a very clever idea as to what function is best suitable to be a solution to begin with, and that being an exponential function. But at this point here, we'd say, well, hold on a second, it's equal to 0, and an exponential function will never be equal to 0 for any real value, so we turn our attention immediately to this polynomial on r. So we focus on just r squared plus 6r plus 9 equals 0. And if we can factor, we want to factor, and here it looks like we can factor. We get r plus 3 times r plus 3 equals 0. So now in this case, I do get two roots, but it's a repeated root. I get r equals -3, and I get another r equals -3. Now let me try to explain what's happening in this description above with our theorem. I think it's great to sort of read it over, but maybe after we see some examples in this lecture, we'll be able to sort of tie it together and make more sense of it. The idea is that when I go to build my solution, so now we're looking at this, and if I was just following that very first theorem that we had, we would say, okay, so what is this trying to tell me? It's trying to tell me that the two solutions that I have of the form y equals e to the rx are y sub 1 equals e to the -3x, and y sub 2 equals e to the -3x. The problem, though, is that these are not linearly independent. It's the same thing. And if I don't notice that right away, or if I'm not noticing it quite yet, when I go to use my superposition principle, we would say, okay, so then what is this? It's c sub 1 e to the -3x plus c sub 2 e to the -3x. But I want you to notice that even though we have two things written down, it's really just one thing. In fact, if I wanted to, I could factor e to the -3x out and collect c sub 1 plus c sub 2, but since these are unknown coefficients, I could really just write this as some coefficient c sub 3 e to the -3x. So although it might appear like two things, it's really just one thing that I have written down currently. So this isn't really the way that we want to go, right? We can see that we're supposed to have two solutions here, But treating it like this, I really don't have two solutions, I just have one. So what do? We cross it out in red. We leave it there as a reminder of where we've been, but we look to the future to remember that we are not our past, and we can always change, we can be better, we can do better, stronger, smarter. All of those things are words that I would use to describe you. Yes, you. So what do? What's our fix for this? Because this isn't going to work. We saw that's not going to fly. Well, it's a really quick fix. We'd say one of them is fine because one of them has nothing to compare it against, so I can't say, oh, you're wrong. But it's when I introduce the second one that we say, well, hold on a second, you're not any different. You're the same exact thing. So we go to this one here and we introduce a factor of x. That's going to fix it up for us. That's going to allow these to be linearly independent so that we're getting everything that we want, everything we could dream of out of this solution to our homogeneous differential equation. Now, what the formula is saying, I want you to notice that we had multiplicity 2. So I have the first one I get for free. The second one, I have to introduce an x to the power of 1, or an x into as a factor. If this had multiplicity 3, I would have another one. So let me do this in another color to illustrate it. Let's say I had another one of these roots. I had r equals -3, r equals -3, and another r equals -3. Then I would tack on to this c sub 3 x squared e to the -3x. And if I had a fourth repeated root of r equals -3, I would tack on to that c sub 4 x cubed e to the -3x. And we don't have that much multiplicity here, so we just really need these two, but that's the trend that we would follow. So whatever that multiplicity is, we would keep introducing factors of x. We get the first one for free, so nothing funny there. We keep introducing these factors of x until we're exactly where we need to be with all of our repeated roots accounted for. So that's the idea here with the repeated roots, is we can't just get away with the same tricks as we did before, but the fix is just to introduce a factor of x. I think a great question is why. Let me know if you'd like. I'd be happy to introduce a separate video talking about why we introduced that factor of x for the repeated roots and how that fixes the problem. But just to keep this lecture sort of short enough, we'll go through the examples. I'll explain it as best as I can. But if you're more interested in sort of an idea behind this, something more along the lines or context of a proof, let me know, because I want to provide that content for you. I'm just not going to do it if you aren't sort of interested. Maybe you are. I think, let me know on Piazza, because I want to do it, but I want to know if you want also for me to do it. So here's the idea, is that I want to try this again. Here I have a new differential equation, 4y double prime minus 12y prime plus 9y equals 0. And I want to start making those substitutions. And after we do this a lot, we start to notice what we're doing. It becomes a lot quicker. It almost becomes sort of second nature. So if I make these replacements, and we're still sticking with that initial guess, y equals e to the rx, I get 4, and then y double prime, remember that's r squared, e to the rx. Minus 12 times y prime, remember y prime is r e to the rx, plus 9 times y is e to the rx, equals 0. And then remember what we do is we factor the e to the rx out, and we're left with 4r squared minus 12r plus 9. And we sort of ignore this e to the rx, right? We say, well, let's just focus on this polynomial on r, 4r squared minus 12r plus 9 equals 0. Now, there are some options here. You could go ahead and use the quadratic formula. I think that's great. I love it. I couldn't imagine where we would be like as a society without the quadratic formula. But this is another opportunity to talk about factoring a bit. For something like this, where my leading coefficient is not a 1, in this case it's a 4 in front of the r squared, I can use what's known as factoring by grouping, also sometimes referred to as the cookbook method, where I take this leading coefficient and I multiply it to this trailing constant. So if I do that, I get 4 times 9, which is 36. And I'm looking for factors of 36. So I want factors of 36 that add to negative 12. And I think negative 6 and negative 6 are the ones that work, right? Negative 6 and negative 6. If I multiply them together, gives me positive 36. If I add them together, gives me a negative, gives me a negative 12. And what I want to do is I want to use those two numbers, to rewrite the middle term. And if you've seen this, it might be a while since you've actually used it, because this is a very much so a pre-calculus topic, but a very cool one. Let me know on our discussion board for our class if you think this is kind of cool. We're going to rewrite the negative 12r as negative 6r minus 6r. That's where these numbers come into play. So here they just happen to be the same, but if they were different, I would still use those two numbers to rewrite that middle term. And this allows me now to do what's known as factoring by grouping, where I want to kind of mentally separate the first two terms from the last two terms, and I want to factor in those. So for the first two terms, I'm looking to factor. Looks like I can bring out a 2 and an r. So here, if I factor out a 2r, I'm left with 2r and then minus 3. And if I, distribute back in, I get back to those first two terms. Now what I want to try to do is I want to look at the last two terms, and I want to factor here as well, but my goal is to factor so that I get the same stuff in the parentheses as I did over here. So I still want to have a 2r minus 3. So what could I factor? Looks like I could bring out a negative 3. And let me just check to make sure I didn't mess something up. If I distribute back in, negative 3 times 2r is negative 6r. Negative 3 times negative 3 is positive 9. But now we can finish this with what's known as factoring by grouping, since this 2r minus 3 in parentheses appears in both terms. That means I can actually factor it all the way out. So factoring that all the way out in front, 2r minus 3. And then I want to write all the stuff that's left over, sort of left behind in the last set of parentheses. That just so happens to also be a 2r and a minus 3, sort of laying about. Which starts to show me that I have another one of these repeated roots happening. You could factor this with a guess and check. I don't think you have to do factoring by grouping, but I think it is sort of the nicest way if you're looking for a method behind what we're doing. Guess and check is nice, but you are really relying on a guess and check method as opposed to some, method with actual steps. So setting this equal to 0, that means 2r minus 3 equals 0, which means 2r is equal to 3, which means r is equal to 3 halves. And this is a repeated root. So for repeated roots, I like to just write them out as many times as they occur. So of course, you could write r equals 3 halves with multiplicity 2. However you want to sort of convey that information. I find that I do my best when I write them out as many times as they appear, so I can keep in mind that's how many pieces I need to my solution. So with these repeated roots, and let's practice what we said, I can start building my solution. Remember, r is the coefficient on an exponent of an exponential function. So we'd say, okay, our solution then is y equals c sub 1 e to the 3 halves x plus, I got another one, so that's c sub 2 e to the 3 halves x. But is this okay? Did I mess something up? I can hear you're all screaming at your laptop screens right now. I got a problem because these are not different. They're not linearly independent. In order to make sure that I have these two linearly independent solutions, I have to go here and introduce a factor of x. And that fixes the problem. This is going to be my solution. This is the trick that we use when we have those repeated roots. We start introducing factors of x to make sure that we have distinction between the pieces of our solution. There's one more type of thing that could happen in general with our characteristic equation. We'll see lots of different types of scenarios appear. But if I don't have distinct roots, if I don't have repeated roots, then it's possible that I have complex roots. And we've all worked with the quadratic formula. We all know that sort of chill on the back of our neck when we have imaginary numbers. So let's talk about that next. If the characteristic equation, so our polynomial on R equal to 0, if this has an unrepeated pair of complex conjugate roots, a plus or minus bi, where b does not equal 0. I mean, if b is equal to 0, then it's not imaginary, it's not complex. So that's just saying if you really have complex conjugate roots, I don't think it's how you spell conjugate. Oh, okay, anyways. Then the corresponding pair, the corresponding part of the general solution of the differential equation that we have has the form e to the ax times, in parentheses, c sub 1 cosine bx plus c sub 2 sine of bx. And I want you to notice the roles that everything is playing here. A plus or minus bi, a is the real part, and that stays in the exponent of the exponential function. B, the imaginary part, the coefficient on I, with that plus or minus bi, goes inside the cosine and sine functions, and that's where we place our coefficients. Now let's see if we can apply that idea to this next example. So it says find the general solution of this differential equation. And let's start with what we've been doing. Y double prime, we replace that with r squared e to the rx, plus 8 times y prime, replace that with r e to the rx, plus 25 times y is our e to the rx, and equals 0. Now we can factor e to the rx out, or you can divide it on each side. It all breaks down to that we're going to be looking at r squared plus 8r plus 25 equals 0. Well, you could probably do some fancy algebra tricks, but I think there's nothing better than the quadratic formula. I'm going to write it up top here. Negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. And if there's a song that you have to remember it, then sing it to me. I'd like to hear you sing it. And this is going to give me the roots for a quadratic ax squared plus bx plus c equals 0. But of course, we're using it for our quadratic on R. We get these roots. And this is generally how we see this information presented to us, way back in pre-calculus. So I'm going to leave this formula up here, and we're going to go ahead and apply it. So what is b? B is the coefficient on R, that's 8, and I want negative b. So negative 8 plus or minus the square root of b squared, that's 8 squared, minus 4 times a times c. A is the coefficient on r squared. I don't see it. So if you don't see it either, that means it's a 1. And c is my trailing constant, c for constant, c for Corey, that is 25. And this is all divided by 2 times a, so that's 2 times 1. And I want to start working with this. So we say, what does this give me? Negative 8 plus or minus the square root of 8 squared gives me 64, minus 4 times 1 times 25 is 100, all over 2. So we have negative 8 plus or minus the square root of 64 minus 100 is negative 36, all over 2. And we get negative 8 plus or minus the square root of, now for negative 36, I want to try to break this up. I want to say, well, this is going to give me a 36 times a negative 1 all over 2. And I can use the product property of the radical to say this is negative 8 plus or minus square root of 36 times square root of negative 1 all over 2. And for these imaginary numbers, we want to remember that the square root of negative 1 is what we call I. The imaginary number I sort of gives me this unit in the imaginary numbers. If you haven't worked with complex numbers, imaginary numbers before, let me know on Piazza. We can go ahead and take some time to talk about these, but I don't think they're too tricky to pick up, and I think most of you have probably already seen them. But if you haven't seen them, let me know, because I want to talk about them a lot more. So now what I can do is I can work with what I have a bit further. We have negative 8 plus or minus square root of 36 gives me 6. And the square root of negative 1 gives me I all over 2. And now I can actually do the division. So negative 8 divided by 2 is negative 4, plus or minus 6i divided by 2 is 3i. So these are my complex conjugate pairs, my complex conjugate pair of imaginary numbers. And remember, we're saying this is a plus or minus bi. And remember that generic form should be e to the ax, and then in parentheses, c sub 1 cosine bx plus c sub 2 sine bx. So if I go ahead and start writing down how my general solution should look, it's going to be y equals, we're going to have e to the ax, but a is negative 4, so e to the negative 4x. Then get your parentheses. We have c sub 1 cosine of bx, b is 3, so cosine 3x, plus c sub 2 sine of bx, so sine of 3x, since b is 3. And this gives our solution when working with these complex conjugate pairs for the roots. Now, again, same comment as when we talked about the repeated roots. I don't think this is intuitive immediately right away. It does come from Euler's identity. So if you want to see a bit more as to where this pops out of the idea that our solution is e to the rx, let me know on Piazza. I'd like to make that video. I can make a video about the repeated roots and then the complex conjugate pair roots, and you can sort of check it out. Let me know what you think about it. We can have some sort of bonus extra content. But just to sort of keep this video a little bit shorter, we're just going to apply the theorem here. And I think it sort of helps to get used to the mechanics going through the problems at first, and then to start to appreciate a little bit more where it comes from. I think that's a very important part of the course. So let me sort of do that in a separate video if you're interested. But let's take a look at what's going on with this one here. And now we're going to sort of go and use all of the information that we have for this section and take a look at some more examples. So here I have this differential equation, y's fourth order derivative minus 8 times y's third order derivative plus 16y double prime equals 0. And we've seen a lot of this characteristic equation stuff. Let's go back to this previous example and think about what sort of happened. So we had y double prime plus 8y prime plus 25y equals 0. The characteristic equation was r squared plus 8r plus 25 equals 0. There's definitely something we're noticing aesthetically, some similarity between how the differential equation looks and how the characteristic equation looks. So I think it's reasonable to, once we get comfortable with this, to go directly from the differential equation, the homogeneous differential equation, into the characteristic equation. And let me jot down some ideas here. So let's say we have y prime, y double prime, y's third order derivative, y's fourth order derivative. We're going to replace the fourth order derivative with r to the power of 4, the third order derivative with r cubed, the second order derivative with r squared, the first order derivative with r, and then y. Technically, we replace it with an r to the 0 if you want to think of it that way, but you can just replace it with a 1, is the idea. And this allows me to go directly from the differential equation into the characteristic equation. So this y's fourth order derivative, that's going to be r to the fourth, minus 8 times y's third order derivative, that's r cubed, plus 16y double prime, that's going to give me 16r squared equals 0. Now, this of course neglects all of the interesting things that we talked about at the beginning, but we, probably don't want to write y equals e to the rx and differentiate it over and over again every single time. So this is a way that we can move to the characteristic equation pretty quickly. Now right away, I can factor in r squared out of everything. And that leaves behind r squared minus 8r plus 16. And And I want to know, can I factor further? So here, the r squared minus 8r plus 16, sure, I can factor this further. That gives me r minus 4, r minus 4. And here, r squared, you could leave it as r squared. I like to even factor this, even though it seems kind of silly to do this. I would write it as r times r instead of r squared. Because I want to see all of my roots. I'm going to have 4 roots because I have an order 4 differential equation. There should be 4 pieces to my solution. And I don't like to write out the multiplicity. I like to write out the individual roots instead. So here I would get r could be 0. That happens when r is 0. I got another r that could be 0. If you want to name them, you could say r sub 1, r sub 2. Next, r could be equal to 4. And then I have another r could be equal to 4. So we got a lot of repeated roots. I have r equals 0 with multiplicity 2, happens twice, and r equals 4 with multiplicity 2, happens twice. So if I go to start writing my general solution, you would say, okay, so y is equal to c sub 1 e to the 0x plus c sub 2 e to the 0x. But this one is the same as what I already wrote, so I need to introduce that factor of x. Now my next roots are different. It's not 0 anymore, so we start the process over again. So we start fresh. We do need a new coefficient though, so c sub 3 e to the 4x. And then c sub 4 e to the 4x, but this one isn't different than the one directly behind it, so that needs a factor of x. And that's how we build with these repeated roots. Now I just want to go up and clean this because I think you're saying, well, e to the 0x is e to the 0, which is just 1. So this is going to look like y equals c sub 1 plus c sub 2 times x plus c sub 3 times e to the 4x plus c sub 4 times x times e to the 4x. And those are our 4 pieces to our general solution for the homogeneous differential equation. And there we had r equals 0, r equals 0, r equals 4, r equals 4. So not too bad, hopefully. It starts to get a lot quicker once we get comfortable with it. Okay, well, let's take a look at another example, but let's see it with an initial value problem. And so to start here, we want to move this differential equation into a characteristic equation. So remember, y double prime, we replace that with r squared minus 6 times y prime, we replace with r, plus 25y, remember we replace y with 1. Y prime gets replaced with r, so y gets replaced with r to the 0, which is 1, so 25 times 1 is just 25. Or you could say, just if you have a y, then just kind of forget about it. And then equals 0. Now, I'm trying to factor this. I don't think that it's going to factor easily, so I usually don't like to mess around and try to get too creative. If it doesn't look like it's going to factor, I like to immediately go to that quadratic formula. So b is negative 6, so negative b is positive 6, plus or minus the square root of negative 6 squared minus 4 times 1 times 25, all over 2 times 1. And that's going to give me 6 plus or minus the square root of 36 minus 100 all over 2. And that's 6 plus or minus the square root of 36 minus 100 gives me negative 64 all over 2. And I want to think about breaking this up underneath the radical. So I have square root of 64 times negative 1 all over 2. And then using the product property of the radical, I can start to introduce that imaginary number I. So 6 plus or minus square root of 64 times square root of negative 1 all over 2. So then 6 plus or minus square root of 64 is 8. Square root of negative 1 is that imaginary number I all over 2. And now I can go ahead and reduce this, right? 6 divided by 2 gives me 3 for the real part. Plus or minus 8 divided by 2 gives me 4i. And this is of the form a plus or minus bi. And remember, when I go to write this, I don't really have room here, but let me just sort of squeeze it in. It's that e to the ax c sub 1 cosine bx plus c sub 2 sine of bx, just as we're getting used to that imaginary form. So here when I go to write my general solution, I just have to plug these things in, as the theorem said. So y is equal to e to the ax, but a is 3, so e to the 3x. And then in parentheses, c sub 1 cosine of bx, b is 4, right in front of I, plus c sub 2 sine of 4x. And that's what I get for y. Now we're not going to stop at this general solution because we have these initial values to work with. So we can actually build a particular solution to the homogeneous. That means I'm going to need y prime. So let me find y prime. I'll leave some space underneath to work with. But for y prime, I can start by rewriting e to the 3x. The derivative of cosine of 4x gives me negative sine of 4x times 4. So there's chain rule there. So I get negative 4 c sub 1 sine of 4x plus derivative of sine of 4x gives me cosine of 4x times 4. So that's 4c sub 2 cosine of 4x. And then I add to this, for the rest of product rule, now I'm going to rewrite that second factor. So here I'm just going to rewrite c sub 1 cosine 4x plus c sub 2 sine of 4x times the derivative of e to the 3x, which is 3e to the 3x. And I probably wouldn't try to simplify it. Certainly you can, but we're just going to be plugging into our, find our initial conditions and work with them. So probably okay to just leave it like this. We have y0 equals 3. So if I plug 0 into y, we get e to the 0, c sub 1 cosine of 0, plus c sub 2 sine of 0. Remember, e to the 0 is just 1. Cosine of 0 is 1, so I get c sub 1 times 1, plus, but remember, sine of 0 is 0. So actually, plugging 0 into all of this just leaves me with c sub 1, and my initial value said that y0 is equal to 3. So that means c sub 1 is equal to 3. So maybe not as bad as it looks. The next initial value is y prime at 0 equals 1. So now that I have y prime, I can plug 0 in for x, so y prime at 0. Remember, e to the 0 is just 1. Sine at 0 is 0, so that's 0, plus 4 times c sub 2 times 1. Plus, here we have 3 times e to the 0, so that's 3 times 1. Cosine at 0 is 1, so I get c sub 1, plus, remember, sine at 0 is 0. So even though I didn't simplify this, it still evaluates pretty quickly, I would say. Here I get 4c sub 2 times 1, which is just 4c sub 2, plus 3 times 1 is 3, times c sub 1 is 3c sub 1. And that initial value said y prime at 0 is equal to 1. So I can set that equal to 1. But I know that c sub 1 is equal to 3. So I can plug that in, right? So 4c sub 2 plus 3 times 3 gives me 9 equals 1. Or that means 4 times c sub 2 is equal to, if I subtract 9, 1 minus 9 is negative 8. And then, hey, dividing by 4, yeah, we get c sub 2 is equal to negative 2. So we have c sub 1 is 3, c sub 2 is negative 2. And now I can go and I can write out this general solution in terms of a particular solution to the homogeneous. And just enough space for it, right? So we have y equals e to the 3x times, in parentheses, now it was c sub 1 cosine of 4x, but c sub 1 is 3. So 3 times cosine of 4x plus c sub 2, which is a minus 2, times sine of 4x. And there we have our particular solution using that general solution and using the initial values to solve for C1 and C2. Looks great. I'm very happy with how that turned out, actually. Yeah, looks nice. Let's take a look at another initial value problem. Just a little bit left in the lecture. We'll try to get through it. So here I want to start by finding that characteristic equation. So here I have 3, and then y's third order derivative should be r cubed, replace it, plus 2 times y double prime, I can replace with r squared, equals 0. And then here I can factor in r squared out, and I'm left with 3r plus 2 equals 0. I can go ahead and solve for r. So here I have r equals 0 twice over, so let me write it twice. R equals 0, r equals 0. If I solve this, subtract the 2 over, divide by 3, we get r equals negative 2/3. And these are my 3 roots. So I want you to notice, since the order of the differential equation is 3, we should have 3 pieces to our solution to the homogeneous differential equation. I have 3 initial values to help me solve for 3 unknown constants. But let's go ahead and start building our solution. So here, I could go ahead and start with r equals 0, so that's going to give me c sub 1 e to the 0x. And I have another 0, so that's c sub 2 e to the 0x, but you're going to tell me, hey, that's not good, multiply it by a factor of x to fix that repeated root situation. And then I have a different root, so I just go back to what I was normally doing, and I can write c sub 3 e to the negative 2/3 x. And I would say to clean this up for sure, since e to the 0x is e to the 0, which is just 1, so we get y equals c sub 1 plus c sub 2 times x plus c sub 3 times e to the negative 2/3 times x. Now I can start working with my initial values, but I'm also going to need y prime and y double prime for my general solution. So no better time to do it than right now. So y prime, derivative c sub 1 is 0, so skip over it. Derivative of c sub 2 times x is c sub 2. And then derivative of c sub 3 times e to the negative 2/3 x, just a bit of chain rule. So c sub 3 comes along, and we get e to the negative 2/3 x times negative 2/3. And then for y double prime, derivative of c sub 2 is 0. But then here, differentiating this again, well, my coefficient comes along, so c sub 3 comes along, negative 2/3 comes along, but wait for it. We have e to the negative 2/3 x times another factor of negative 2/3 from chain rule. And that negative 2/3 times another negative 2/3 gives me a positive 4/9. So there's y double prime. And now we can start working with our initial conditions. So what do we have? Y at 0 equals negative 1. So here, if I were to plug 0 into y, I get c sub 1 plus c sub 2 times 0 is 0, plus c sub 3 times e to the 0 gives me c sub 3. So that just gives me c sub 1 plus c sub 3. And what is y at 0 equal to? It's equal to negative 1, is what the initial value says. So hold on to this. We're going to have to come back to it and work with it later. But what is our next initial value? It says y prime at 0 equals 0. My favorite, lots of zeros, right? So here, y prime at 0, if I plug 0 in for x, I get c sub 2 minus 2/3 c sub 3 times e to the 0, which is just 1. So I get c sub 2 minus 2/3 c sub 3. And this is equal to 0. So I got to come back to that. And one more to work with, and I think this last one's going to be the nicest. Y double prime at 0 equals 1. If I plug 0 into x, so for y double prime at 0, I get e to the 0, which is 1, times c sub 3 times 4/9. So that's 4/9 c sub 3. And we said this is equal to 1. Which I can solve this, right? So we can solve this here. If I multiply both sides by the reciprocal, you see, well, then c sub 3 would be equal to 9 over 4. So I have one of them. And this is great because that means I can actually go to, either one of these next. So let me go to this next one right up above it, and I can solve for c sub 2. So here we would say, okay, well then c sub 2 is equal to 2/3 times c sub 3. Well, that's 2/3 times c sub 3 is 9 over 4. And I can reduce here across the fraction. So c sub 2 is going to give me 3 over 2. And then I can go back and solve for c sub 1. So I'm going to use some of this space up above that I've saved. C sub 1 is equal to -1 minus c sub 3. But we showed earlier that c sub 3 is 9/4. So c sub 1 is -1 minus 9/4. But get a common denominator. So this -1, I can write it as -4 over 4, like that little trick there. And then c sub 1, I'll go ahead and combine these as like fractions. That gives me -13/4 for c sub 1. And I have it all. So now I just want to go back to this general solution that I had and rewrite it in terms of these new coefficients. I know what the coefficients are now, so I know everything about my solution. So I shouldn't call it a general solution anymore. It's now going to be my particular solution. So y is equal to, first, it was c sub 1 by itself. That's -13 over 4. Plus c sub 2 times x. C sub 2 is 3 over 2. So 3 over 2 times x. And then c sub 3 e to the -2/3 x. C sub 3 is this 9/4. E to the -2/3 x. And this looks great right here. There is our particular solution to the homogeneous differential equation. Using that characteristic equation, let me know if you like this characteristic equation, if you think it's cool, if you think it's not cool, let me know. We'll take a look at just a couple more examples. These next ones get a little interesting, a little fun. It says find a general solution by first finding a root by inspection and dividing. This can kind of be a scary thought, but let me talk about it. First, let's get that characteristic equation. So I know the third order derivative of y can be replaced with r cubed. And then plus 3 times y double prime can be replaced with r squared. And then -4 times y, remember y we replace with 1, or we just ignore it. So this is my characteristic equation. R cubed plus 3r squared minus 4 equals 0. Now it's kind of scary to say find a root by inspection, because that means we want to kind of stare at this and try to find a value that's going to work for r. So pause the video, look at it a bit, let me know what you think is going to work for r. And a hint I can give you is if we're ever finding a root by inspection, hopefully it's a nice number that's not too crazy, it's not far outside of our reach or the realm of possibility. Is that true in the real world? I mean, your root could be anything, right? It could be a crazy number that you would never even think of. But for problems like this that I'm gonna do with you, I don't want to have anyone, in pain. Don't click off the video just yet. I want you to stay with me. So the idea is that it's hopefully going to be a relatively nice number to find. What did you decide? I'm looking at this, and hopefully I don't have to look too far to realize that r equals 1 is going to be a solution. That if I have 1 cubed plus 3 times 1 squared minus 4, that gives me 1 plus 3 minus 4 gives me 0. So if r equals 1 is a solution, try to think backwards. That means r minus 1 is a factor. Right? Because what do? We factor it, and then we set the factor equal to 0. So if we had r equals 1, that really came from r minus 1 equals 0 as a factor. So now that I know a factor, what I can do, and I think you're going to like this a lot, is I can do polynomial division. So I want to take my r cubed plus 3r squared I would write in a 0r since it's missing. I want to have space for it. Minus 4. And this is my dividend. I want to divide by my divisor, r minus 1. And I want to find my quotient as a result of this. Let me know on the discussion board if you like division of polynomials. And so the idea, just like long division, I want to take the leading term of my dividend and divide it by the leading term of my divisor to determine what goes on top. Or you can sort of think about it intuitively too. Think what times r gives me r cubed. Either way, you should have r squared for the first term in the quotient. Now what we do, we take that first term in the quotient, multiply it through the divisor, and write that underneath. So r squared times r minus 1 gives me r squared times r is r cubed. And r squared times minus 1 is minus r squared. Now remember, with long division, we want to subtract. And remember to distribute your subtraction. R cubed minus R cubed gives me 0, which that's why we picked it, so that should always happen. 3R squared minus negative R squared gives me a positive 4R squared. And drop the rest down, plus 0R minus 4. So now we're looking at the 4R squared minus 4 is really what's left. And we treat this as a new dividend, and we sort of go through the algorithm again. So now I can take this leading term of my new dividend, divide it by the leading term of my divisor. 4r squared divided by r gives me 4r. So I go up here and I write 4r in my quotient, and I go through the same steps again. So now, yeah, good suggestion. Let me get another color. 4r times r minus 1. 4r times r is 4r squared. 4r times minus 1 is minus 4r. And subtract in between. Notice 4r squared minus 4r squared gives me 0. That's why we picked it. 0r minus negative 4r gives me plus 4r. And then minus 4 I just bring along down. And then we start this process again. So now I want to look at this and think, okay, 4r divided by r, well, that should be 4. And then multiply this last piece of the quotient into the divisor. 4 times r minus 1 gives me 4r minus 4, and then this should subtract out cleanly. So we have now a factored version of this, partially factored. What we're saying is that r cubed plus 3r squared plus 0r, sure. I started writing it already, so why not? Minus 4 can be factored into r minus 1 times r squared plus 4r plus 4. But then this can factor further, so now we know that we can factor even more. So now sort of the secret has been unveiled, the curse has been lifted. We would have r minus 1 and then r plus 2, r plus 2. Or we see that we have roots. Keep switching colors like I'm crazy, but I want to make sure that all of this is clear in your notes. We have roots of r equals 1, r equals negative 2, r equals negative 2, which means that now we can write our general solutions. Let me use this space that I have left. The division took up a lot of my space. So we get y equals c sub 1 e to the 1x plus c sub 2 e to the negative 2x plus c sub 3x e to the negative 2x for that repeated root. And there we have, in this beautiful red, our general solution. But we had to first find a root by inspection, and then we had to start dividing polynomials. Oh, I did have all this space down here. Okay, well, look it. I think we got one more left, but this is sort of a personal thing to me now. I got this space left over. Yeah, yes, 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 yes. Looks great. I'm having a good time. Let's take a look at, looks like just a couple left. Let's take a look at another one very similar. Find a root by inspection and dividing. Let's talk strategy here. Get that characteristic equation right away. R cubed plus 27. Remember y, get rid of it. Y prime is r, y double prime is r squared, y's third order derivative is r cubed. Pause the video, try to find a root by inspection. Hey, welcome back. What'd you get? I'm looking at this one. I'm not trying to go too crazy. I'm not trying to do anything that's like, you know, off the walls here, but I'm thinking r equals -3 is going to work. -3, if I cube it, is going to give me -27, plus 27 is going to give me 0. So it looks like we got a good idea right away. Hopefully you were able to find that. You know, certainly the more you do this kind of activity, the easier it becomes. But if r equals -3 is a root, that means that r plus 3 is a factor, which means that I can now go into some polynomial division. So what we can say is I can take, to be a dividend, this r cubed, and I'm going to write in the missing terms 0r squared, 0r plus 27, and my divisor is going to be r plus 3. Go ahead and try that long division for the polynomial. Let's see what we get. Take the leading term of the dividend, divide by the leading term of the divisor. R cubed divided by r is r squared. Multiply through the first term of the quotient into the divisor. So we get r squared times r plus 3 gives us r cubed plus 3r squared. Make sure you're subtracting all of it. So r cubed minus r cubed is 0. 0r squared minus 3r squared is a minus 3r squared. And drop down those trailing terms. So now we go again. So now leading term of my new dividend, -3r squared divided by r, gives me -3r. And then multiply that through. So -3r times r is -3r squared. -3r times 3 gives me -9r. Subtract all the pieces. -3r squared minus -3r squared is 0. 0r minus -9r, so be careful there with the signs, gives me positive 9r, and then drop down to 27. And then we'll go once more with this. 9r divided by r gives me 9. And then if I multiply through, this is actually going to work out perfectly. 9 times r plus 3 gives me 9r plus 27. And going through and doing that last bit of subtraction leaves me with a clean division, a remainder of 0, which is telling me here that I can factor this fully, that my r cubed plus 27 is equal to r plus 3 times r squared minus 3r plus 9. So there we have everything factored. Now I would want to try to factor this even further. I want to think about this as a characteristic equation, set it equal to 0. But looking at this, I don't really think that this quadratic is going to factor nicely. So I would immediately go to the quadratic formula and take a look at that in red. So I'd say negative b is -3, which is 3 plus or minus. Square root of -3 squared is 9, minus 4 times 1 times 9, all divided by 2 times 1. 3 plus or minus the square root of, I might even just factor a 9 out, and I'm left with 1 minus 4, all divided by 2. So we get 3 plus or minus square root of 9 times, this is going to give me -3, but I could say 3 times -1, all over 2. And use that product property of the square root. So 3 plus or minus square root of 9 times square root of 3 times square root of -1, all over 2. So I don't know what you're thinking. I'm thinking 3 plus or minus 3, radical 3i, all over 2. Or we could even break this up a bit to say 3/2 plus or minus 3 radical 3 over 2 times I. And that is our a plus or minus bi. Don't forget, I had a root to start with r equals -3. So I'm also going to make myself a note. Also, r equals -3. We found that root by inspection. So now when I go to write my solution, let me start with the complex part, because that's going to give me the cosines and sines. So we get y is equal to e to the 3/2 x. Remember that real part goes in the exponent of our exponential term. And then parentheses c sub 1 cosine of bx. So that's 3√3 divided by 2 times x, plus c sub 2 times sine of 3√3 over 2 times x. And I got one last term, so we'd say plus c sub 3 e to the -3x. And there we have our general solution. I think we've been looking at a lot of this characteristic equation stuff now. Let me go ahead and just talk very briefly about this last problem, and I'll leave it as an exercise for you to try on your own. It says one solution is given, find the general solution. So I want you to consider this, that if this piece is given, and we know there should actually be 3 pieces since we have a order 3 differential equation, think about this as e to the rx. And this is trying to tell me that one of the roots, r, is 2/3. So from that information, I can work backwards, I can find the factor, and I can do that polynomial division. Try doing that, see if you can find the general solution here. Let me know what you get over on our discussion board, and I can let you know if it's looking good or not. This one can be factored, but I would encourage you to try doing the polynomial division instead of trying to factor it, just to get that extra practice in. But let me know what you get for this one. So we'll say this is going to be a try it before you buy it. Yeah. That is it for the section. Let me put the homework in the homework jar. Please take a look at the homework over on our online homework platform. Hey, it's been great. I love that characteristic equation. If you've stuck with me through the very end of this video, I want to say thank you so much. Let me know over on Piazza that you made it through the entire video, and let me know what you think about this characteristic equation. But no matter what you do, make sure that you keep learning, keep dreaming, and make sure that you follow your heart. And I'll see you next time.